Welcome back to multivariate calculus. In this video, we're going to be looking at a change of coordinates for a function of several variables. We've looked previously at several different coordinate systems that can be used for functions in 2 and 3-dimensional space. In 2 dimensions, we have the rectangular coordinates and the polar coordinates. In 3 dimensions, we have rectangular, cylindrical, and spherical coordinates. There are also alternate ways that we can set up the coordinate systems we already have. Some of these ideas are very important in physics. Let me get my head out of the way and I'll sketch out a quick example. If we think about our usual coordinate axes, our usual x and y direction, we'll just do this in 2 dimensions just to make life easier. If we are looking at a situation which involves, say, a ramp and a block sitting on the ramp, we might look at the forces acting on this block, right? There's the force of gravity pointing downward. There's the the normal force keeping it from falling into the ramp. There is, of course, I'm going to assume it's sliding down the ramp, so there's some friction pointing this way. And maybe it's on a spring, in which case there's a force pointing this way as well. And in the usual x and y coordinates, these forces are all over the place and really messy. But if I just set up a new system of coordinates, where I set this as my u-axis and this as my v-axis, and to get from here to there involved a translation and a rotation, all right, so to figure out a coordinate in my u-axis, I'm going to first add some x naught. And then I'm going to take, well, in my x direction, I'm going up, assuming this is some angle. I can figure out that that's going to be x cosine theta, but also upward is going to be important. So I'm going to have some y sine theta action going on there as well, and etc. All right. Actually performing the change of coordinates and figuring out how things are figured out here is beyond the scope of this course. That's something that you may have seen in a trigonometry or pre-calculus course. That's something that you may have seen in a physics course. For our purposes, knowing that it is a thing that exists is good enough. Instead, what we're looking at is we have a new system of coordinates that are given as u and v. So we have x is some function of u and v, and y is some function of u and v. And I'm going to take my function of x and y and think about x being a function of u and v, and think about y being a function of u and v, which gives me a new function f, which is really just a function of u and v. Well, this setup is basically the same thing that we had in our path derivatives. If I wanted to take the derivative of f with respect to t, where x and y were both functions of t, I used a chain rule. I'm not going to go through and prove it because the math looks so incredibly similar, but I claim that the partial derivative of f with respect to u can be calculated by taking the partial derivative of f with respect to x and multiplying that times the partial derivative of x with respect to u, and adding to that the partial derivative of f with respect to y times the partial derivative of y with respect to u. And again, I want you to think about this and the analog. Of the change of variables we used. When x and y were a function of a single variable, this was fairly straightforward. We had ordinary derivatives. Now that x and y are functions of two variables, we end up with partial derivatives. So we can take the partial of f with respect to u. We can also take the partial of f with respect to v. And as we've seen previously, if we extend this into 3 dimensions, that's still going to be the case. If I have f of x, y, and z, where x is a function of u, v, and I guess w if I need another letter. Likewise, y is a function of u, v, and w. Then I can write that the partial of f with respect to u is the partial of f with respect to x times the partial of x with respect to u plus the partial of f with respect to y times the partial of y with respect to u plus the partial of f with respect to z times the partial of z with respect to u. And like I said, coming up with the change of coordinates is not something that I'm all that interested in this course. Once we have the change of coordinates, being able to apply it is the thing that I'm interested in. So let's look at a relatively straightforward example. That being the cylindrical coordinates. X is r times the cosine of theta, y is r times the sine of theta, and z is z. With that, if I have some function, and I want to think about this function in cylindrical coordinates, even though it's given to me in rectangular coordinates. Well, I can take the partial derivative of this function, say with respect to theta. In order to do that, using the chain rule, I guess before I even get into that, I could choose to simply plug in x equals r times the cosine of theta, y equals r times the sine of theta, and go through like that. And it would work. There's nothing wrong with doing that. But hopefully, by building up something with the chain rule, we'll be able to develop some structures that will help us later on. And of course we will. I wouldn't be doing this if we couldn't, but you don't know that yet. When you're thinking about the development of calculus, why did we try to build this up instead of just plugging things in? Because we were hoping that it would build up some ideas that we could be able to use later on, and it would let us do some powerful things in the future. All right, so using the chain rule, we should have the partial of f with respect to theta is the same thing as the partial of f with respect to x times the partial of x with respect to theta, plus the partial of f with respect to y times the partial of y with respect to theta, plus the partial of f with respect to z times the partial of z with respect to theta. All right, this is a function that we have looked at before. The partial of f with respect to x is going to be 2x minus yz. and the partial of x with respect to theta. The derivative of r times the cosine of theta is going to be minus r times the sine of theta. Partial of f with respect to y is going to be 2y minus xz, and the partial of y with respect to theta is going to be r times the cosine of theta. And then we can find the partial of f with respect to z, but notice that z itself does not depend on theta, so the partial of z with respect to theta is 0. That term goes away. Then we have x, y, z's, r's, and thetas all going on. That's too much. So we have to replace x with r times the cosine of theta. We have to replace y with r times the sine of theta. Then we will distribute. So we'll get 2r squared. I guess there's going to be a negative here. Negative 2r squared sine theta cosine theta minus a minus is plus r squared z sine squared theta. And then we'll have 2r sine theta times r cosine theta, which is going to be plus 2r squared sine theta cosine theta. And then we'll have minus r squared z cosine squared theta. Notice here we have a minus 2r squared sine cosine. We have a plus 2r squared sine cosine. Those things cancel each other out. And we're left with r squared z sine squared theta minus r squared z cosine squared theta. All right. So sine squared and cosine squared, but unfortunately it's subtraction instead of addition. We could simplify this so that theta appears only once. We could factor out the r squared z. I don't know that those things make it any better or not, so I'm not going to bother with it, but that is a thing we could do if we so desired. But I'd like you to look at something that involves a less standard change of coordinates. Let's define that x is equal to u times the natural log of v, and let's define that y is equal to v times the natural log of u. And let's look at a function f of x and y equals e to the x minus e to the y. I would like you to find the partial derivatives of f with respect to x and y. Then I would like you to find partial of u of x with respect to u and partial of y with respect to u. And then finally, I'd like you to find the partial of f with respect to u. And again, as I've said before, I would like you to take the time to find this in two different ways. First, use a direct substitution to evaluate that, and then also use the chain rule, just to see that, yes, in fact, these two things do give you the same value. All right, so take a few minutes to play around with that one, see where you end up with, and I'll see you in the next video.